So this is a little introduction into this course. It tells you a little bit what is this about, what the problems are. So it has some value of its own because I will be sketching a little bit what the research frontiers in autonomous robotics are. So first thing, if you know, what do people actually think about when you say robotics? You know, what happens? Actually, I did a Google search with that word. I did it 3 years ago, and I also did it actually just yesterday, and the results are very similar. So this, if you click on images, this is what you get. The first page you get when you type robot into Google. Okay, kind of really interesting. These are the first entries. These are all humanoids, right? None of these are actual robots that are used for anything other than toys or research. And humanoids are human-like robots. They usually don't do anything interesting. They just look like they are humans. And it was then on page 2, and then I think yesterday I saw that on page 1 already you get one-legged robot. I think right now you get the Boston Dynamics dog-like robots. Forgot its name right now. That is actually somewhat real because people are using that, not really deployed, but at least using it for advanced research. And then you get maybe like a vehicle as well, and then maybe you get a robot arm. These are actually compliant arms that are also not standard. So you don't find actually the robots that are deployed worldwide in industrial robots until pages later. At that time on page 4, right? So that's already interesting, right? The notion of robotics comes from the history of that term, which is essentially emulating humans, and that was originally the idea. Some of you might know it goes back to some Czech playwright who used that term for the mythical idea of the golem, right? A non-alive thing that you turn alive that's human-like. That's pretty much the idea. That's of course totally unconnected to the reality. The reality is that there are enormous numbers of robots in the world, and most of those are not autonomous. They are certainly not humanoid. They are just programmable machines. Right? Robots, industrial robots are machines, and they are less special purpose than most other machines. That was originally the idea of what robotics is. And so I'll talk about, this course is not about that, right? There's a little bit of overlap with that. That is, these programmable machines share some features, and I'll come back to that with what you do when you have autonomous robots. And so there will be 2 or 3 lectures that actually are from standard robotics textbooks in the more traditional sense. So that is certainly the reality of robotics, right? Almost all robotics is like that. And I'll now review the autonomous part. So let's get you the flavor for that. So these are some images. These are also not very new. These are the most common autonomous robots are vehicles. These are the simple things. I actually own one of those, these vacuum cleaners, you can buy those. And there are lawn mowers like that, and pool cleaners and things like that. There are vehicles that are deployed in industry for that. So here are some of the vehicles I will be referring to. Like this on the left is one that will show up in one lecture that we built 25 years ago in Marseille. Very cheap and simple, kind of interesting one. This is one that my student, actually this was also in Marseille. I'll refer to that. And then we actually built also a autonomous wheelchair in Marseille, also again 20 years ago, which was actually very cool, very good. I will not really talk much about that. So that's vehicles, and of course there are a lot of real-world applications. There are special purpose vehicles like that. So some of those are actually deployed. That there are in factory floors. You have vehicles, and then of course autonomous driving cars is part of robotics. Right? These are vehicles that control themselves in some sense. And there are certain aspects of that are in deployment, that autonomous driving is not really fully deployed. Actually, I used to do work in this area. Be happy to discuss that. I don't want to make that part of the course. But you could say, if you simplify the environment, then autonomous vehicles are in practice. For instance, some of you might know that these vehicles that serve in certain logistics centers are sometimes called autonomous, and they are deployed. Now, the autonomy is actually very limited. That is, for instance, they will stop if they detect an obstacle, and then they tell the central computer there's a problem. So that's barely really autonomous. Some of these, there's some cases where vehicles would drive around on a factory, in a factory context, and the factory would be prepared for them. Like they have some markers, and they can navigate by recognizing QR codes on different places and so on. And so then a little bit more autonomous. Very often they also just stop if there's a human, for instance, walking in front, so they don't really have real obstacle avoidance and so on. And of course, if you were to drive in the real world with actual non-robotic participants, then you really have to be autonomous. And that turned out to be a little bit harder than we anticipated, as some of you might know. Legged robots are also vehicles. Also, they carry the body and the sensors through the world. There's a lot of interest in those. A lot of them are biologically inspired because animals have legs and not wheels. You could think of wheels as just being like a lot of legs, in a certain arrangement. So it's sort of like a continuum transformation from legs to wheels. And you might have heard I mentioned Boston Dynamics, maybe the most visible company in autonomous robotics. And they have these, it's actually an interesting video right now. They're just switching off their old one to the new one. If you know this, just Google maybe in YouTube, Boston Dynamics, and then you will see some of the coolest legged robots that are around. And they just announced a new generation of that. So this branch of biologically inspired robotics is very prominent in autonomous robotics research, especially for vehicle type robots. There's these sort of special purpose things. There's a lot of special purpose stuff here. Autonomous vehicles in water, in a way, much simpler, right? Because water has not a lot of obstacles and it's very easy to navigate. Even simpler in flying. Actually, most flight machines don't do any obstacle avoidance. For instance, they don't really have any. If they have situational advantages from a central agent, right? Air traffic is controlled centrally. So it's just these sports or the so-called commercial, like flying for fun. Those people have to look out to fly visually, but almost everything is controlled centrally. So autonomous flying isn't really a big problem, and in the military it is very, very successful, but it's very uncharacteristic of autonomous problems, and that reflects one thing, that autonomy has to do with acquiring information about the environment. I will be more formal about that in a minute. And the environment on the sea and in the air is quite homogeneous and doesn't have a lot of objects in there, while terrestrial environments are much more complex and very difficult to estimate or model. And there are degrees there, right? Vehicles, for instance, their environments are streets, and those are relatively simple. While if you're indoor and you're maybe interacting with humans or operating on objects, then it's much more complex. And again, there you can have degrees, right? The ideal vehicle has a limited environment would be an environment where there are no humans, and it's all just marked things, for your device. For instance, there are some of these autonomous trains that go on tracks, and they only maybe have some detector if there's some obstruction, and then again they will stop. And that's a much simplified environment. Then it's much easier to be autonomous. So this is vehicles, and then there's the other side, which are arms, hands, or also manipulators, as we call them. So these are two different categories, and that has some real theoretical meaning. So essentially, the difference between a vehicle and an arm. What's the difference between vehicle and arm? Anybody have an idea? Seems obviously different, right? But what conceptually makes a arm and
Vehicle is more for transporting something.
Yes.
Transporting themselves, and arm is more for interaction.
Right. That's certainly true. Now you could have an arm mounted on a vehicle, and how would you know it's the arm component? That was another
I wanted to say that it doesn't really move in space like a vehicle would. It only has a local range that it operates in.
Yeah, that is certainly true. So you can say the conceptual difference is that a vehicle is a system in which the sensors through which you find out about the environment are moving with the actuator. So the vehicle moves, and the important thing is the sensors. We'll talk about autonomous means that you control your behavior based on sensors that you have yourself as the robot. The sensors are moving with you, while the arm, that's not the case. So for instance, if you put a camera into your arm, then you are more like a vehicle. In fact, there is a branch of manipulators that's called visual servoing, where you actually control an arm by a camera in the arm, and you steer it, for instance, just to say, if you're looking for something like a bottle like this here, then you just make sure that that thing grows on your visual array, and then you're approaching it. And that would be a strategy, it's called visual servoing, that would be more vehicle-like. So that's a big conceptual difference between arms and vehicles. So vehicles actually can do a lot of things, and that's why we have a lot of progress there, without ever really decomposing the world into objects. For instance, for a vehicle, ultimately, it's important just to know if there's an obstruction. So for instance, a lot of vehicles work with depth profiles. Like the modern vehicles use laser rangefinders, and they just get a 2D or even a 1D array of depth measurements. And when there's enough depth, there's no obstacle, then you can go there. Maybe they have some recognition of line markers and a couple more things, but they don't have to know. For instance, if there's something on the road, they don't have to know, is this a bicycle or is this a other car? They might have to, for luxury, like you want to brake harder, perhaps for a pedestrian or something. But it's in the first approximation, you don't need segmented information, you don't need object recognition, pose estimation, or anything like that. But if you have an arm, you need that. And you need to estimate, you want to grasp something, grasping a glass, which is transparent. It's really demanding computer vision. And then you have to know, where it is, because you're transforming, you're not seeing it from that hand, you're seeing it from somewhere else. And then you have to sort of compute what configuration the arm has to have if it is there. So it's much more demanding in terms of perception. So that's roughly the reason why you will have deployed autonomous vehicles, including these vacuum cleaners and these things you can buy for a few €100. But there is no autonomous arm that does anything reasonable. So you see some of these humanoids, they don't do anything, they wave their hands. It's just a little program that's running of moving them. If they fall over, they still keep waving their hand. So they have no action-oriented anything in the world. And if they want to grasp something or handle something and so on, then it really is challenging. And then there's, I'll say more about that in a moment. So that's just to make clear why there's this category difference. So the robot arms that are used in autonomous robotics are not categorically different from the robot arms in industrial robotics. But very often you expect, so industrial robots have this very good control. That is, they have, if you give them a configuration, a position where the end effect of the hand is supposed to be, they can achieve that with a very high precision, also very fast. And they do that by control, that is by measuring the error. They have some sensors that detect the pose of the arm and reducing that error to 0. And if they're perturbed mechanically, they just have enough force to overcome that. So they're very strong, for instance, compared to the payload, right? But if you, as a human, you can lift half your body weight. Actually, if you're a little bit fit, you can even lift your whole body weight, and you can maneuver that. Maybe not the piano, but I could even perhaps lift this table here and maneuver it somewhat. While if you take an industrial robot arm, it can control a weight that is less than 1/10 of its weight. It's often actually something close to 1/50 of its weight. And the reason for that is that it is not a very intelligent kind of control. That is, it regulates against any perturbation, and a lot of perturbation comes from its own movement. I'll have a little lecture in the second part of the course about that interaction torque. So if you accelerate one joint, it affects the other joints. And so the acceleration of one joint is a perturbation on the other joints, and you have to compensate for that by making more forces there, accelerations there, and that again perturb the first joint, and this have the whole nonlinear escalation of perturbations that forces them to be so strong. So these industrial robots are very strong and they act energetically against any perturbation. And that is the reason why they are often not so useful for autonomous robotics. Because in autonomous robotics, you will want to estimate yourself where the object is and what a good class configuration is. And any error that you make there might lead for the robot to physically contact the object. And then if you're just insisting on reaching that miscalculated point, then you're going to destroy the object, right? If you put down your robot hand on the table surface and you estimate it wrong and the position you're planning is inside the table, the industrial robot will try to get there and will smash the table and destroy it. That includes a human who gets in the way, right? So that's why you don't want to be in the workspace of an industrial robot because it can kill you. And so the robots that use autonomous robotics tend to be weaker and therefore safer for a human to be around. They're actually still often stronger than the experimentalists working with them. I think we have one here in the robotics lab, which is almost always off. But we also have a little cordon around it because even that robot can do stuff that isn't so nice to be to get hit by that arm. Ultimately, the goal would be that they are compliant. That is, that they would yield when they physically interact with something, that they would reduce the force to yield, to accept that it doesn't get where it's planned to get. This, which is, of course, what we humans do. Also, we are somewhat weak, which makes that we don't destroy objects and we don't destroy our own bones in study, right? You don't usually hit objects so hard that you break your bone. It can happen in extreme cases, but not normally. If any of you know Superman, these cartoons, then you might remember, and if that's maybe more my generation, that when still the cartoons, so the movies are different. That was a little problem that this boy, when he had these superpowers, would always break the doors and break everything. Yes, because if you make a little error, then if you had the super force, you would be breaking objects and also maybe yourself. Right? So we're weak or compliant, soft. There's an area now called soft robotics. It's based on actuators that are in that sense yielding, elastic, and so. And when you have that, then turns out then achieving control, that is getting that robot arm to a particular place in a particular time, for instance, to catch something, becomes a whole issue, a problem. And you will see in the second part of the course, we'll talk about that. We'll talk about timing, how to reach stuff in time, how to intercept things in time, how to do that in a way that is consistent with autonomy, that is not doing it so brutally, being willing to be open to perceptual error, for instance. So that's the only difference. So this is the arm that we have down there, very expensive, and moving very slowly here because we were this faster. This is the old version which we no longer have here. The one is for self-build. And this is a commercial one, which is very, very poor. It's like the best you can get out of it. Now, more like a toy. We also still have that from this weekday event. Yeah. And we used to have so when you combine them, it's a mobile manipulator, right? And that's what I was hinting at. Then the arm is arm-like because the sensors are on the vehicle. They're not in the arm. And we actually had one here. We called it Arnold because it looks like this bodybuilding guy. It's kind of hard to see even. It's not so important. We've actually given up vehicle work, but I'm teaching about vehicle work because vehicle work has moved so much ahead that now this very basic approach that we use is no longer state of the art. So I'm defining a little bit more formally what autonomous robotics means. So autonomous comes from this autonomos, so nomos is law in Greek, and this so giving yourself your own law. So the original idea was, robots are programmable machines that gives them some flexibility, right, much more than a regular machine. And then autonomous robots would be self-programming machines. And that was this idea of autonomous intelligence as programs. So because at that time people were thinking about machines as just being computer programs, and then it would be self-programmed. And in reality, the key issue of that is that you're expecting this self-programming to be flexible through its perception of the world, of the environment. That is, it adjusts its program to something in the world, and it does that in some sophisticated way. I'll say more about that just to, as contrasted to, let's say, an industrial robot that has a fixed program that is not informed about the environment. So for instance, if you take an industrial robot and you just decalibrate it a little bit, like it is shifted, it's mounted, 1 centimeter off, then it will do the same movement. It was programmed, even though every time it hits 1 centimeter to the left of where it's supposed to be, right? It has no way of knowing and making maybe terrible damage. We were in a research project, although a long time ago, with what was then called Daimler Chrysler, which is now again called Daimler, I guess, this Mercedes-Benz company, where we were making a robot arm autonomous. They called it autonomous. It was one of the big robot arms that lift pallets, and do heavy lifting. And the autonomy consisted of increasing the tolerance for decalibration to 1 centimeter. So if you grab a pallet and the pallet isn't positioned perfectly, it was supposed to be able to adjust for 1 centimeter off by having a camera on the arm and then actually sort of detecting whether your arm and the camera is well aligned. While normally, previously, it had to have a position of 1 millimeter, which it actually achieves in special practice. And this thing that we did was way too complicated for them, and they certainly not deployed. It's just a research project to do that. So that little thing of correcting the planning based on visual information was what they called autonomous, and something like, really letting a vehicle decide on its own. They says, yeah, that's crazy. We want to control everything. So that's a little bit where that stands. So this capacity to modify its algorithm, that would be a better way to say it, based on sensory information, that's sort of key. Now, you may know that in control theory, people talk about autonomous control, and because control, control, roughly speaking, is to make sure that a machine does what it's supposed to do, which means that you are measuring, that's the autonomous part, you're measuring what it does compared to what it should do. You're determining the error, and you're doing something to reduce the error to not to zero, but to be some below some bound. And so that's sometimes called autonomous control, because for the same reason that it actually has its own sensor to determine the error or determine the state of the world. And so when we say autonomous robotics, we mean something that's a bit more than that. Now, for instance, these heating devices here are supposed to be autonomous. They have a thermostat, right? The thermostat has a temperature sensor, and it has a set point, and it determines the distance and opens the valve if it's hotter or if it's colder, yes, and so on. And then you would say, well, that's not really autonomous robotics, it's just autonomous control. Now, the difference between those are not very easy to formulate, but perhaps you could see that it becomes more than just control if there's some decision making involved, ultimately. So decision making, what is that? Again, simplest case would be obstacle avoidance. We always think obstacle avoidance is sort of the lowest level autonomous robotics kind of thing, because it's obstacle avoidance involves typically a decision. For instance, minimally as a vehicle, do I go around the obstacle on the left or on the right? As simple as that, right? And that means that there is something critical happening there, and we will actually be discussing this in some detail in the course. It's actually instability. So stability, will define that much more formally, and Lucas will define it mathematically next week, and we'll do a couple of lectures on that for the vehicles. Stability ultimately means something that a small change leads to a small effect. Like if you detect that you're off a little bit, that you're off to the vehicle's avoiding an obstacle on the right, let's say, and the obstacle is misestimated or moved a little bit, then you're correcting your course a little bit to keep avoiding it. But the decision to go around left or right somehow goes through an instability, because at some point you will say, well, with this little shift of the obstacle, now I will keep avoiding it on the right, but I shift a little more and I say, oh no, let's go around on the left. So there will be a small difference that makes a macroscopic, a large difference in your behavior. It would turn really macroscopic amount of turning to go around the other side. Then that's something we would call decision making, right? It will be something where a small change makes a major difference. So it's many decisions are like that, go, no go, was there a signal detection, right? Was there a signal or not? Is there a, like you're shooting down a rocket, right? This is originally actually the military application around which a lot of the theory was developed, was shooting down enemy planes and things like that. We had a radar, and in the Second World War, you determined whether there was a enemy object or not, right? That's a detection decision, right? If this noisy signal, and is this evidence for a plane or not? And there will be a sensitive thing with a little bit more of radar echo, you would say, yes, I decide yes, and a little bit less, you say no. It's a binary kind of decision that you make, and there's actually a very typical thing associated with it, which is sometimes called decision stabilization. That is, once you have decided it is an enemy rocket or airplane, you would actually keep that decision, even if now the signal becomes weaker again. Because once you're committed, you're going to send that rocket no matter what, within certain limits. So I can't formalize that more, but we'll talk about that a lot. And so when we talk about autonomous robotics, we mean this dependence on sensors and this ability to change its behavior, but in this qualitative sense that involves some form of decision making. And that we think even more complex, right? In planning all movements and maybe planning steps of actions and so on. That's where you can see in practice it might become a little bit difficult, because if you allow your robot to decide a lot of things, then maybe it does something that isn't really what you wanted it to do. And that's maybe the other side of that is we still in robotics want to give some kind of instructions or orders to the robot, right? So for instance, you're not, maybe one reason why you're not using your dog as an autonomous robot is kind of difficult to give orders to your dog. You have to train the dog forever, and it only does certain tasks that are close to what it naturally does and so on. Most of the time it does really what it wants, that it serves its own purpose. Right? And that's certainly not what you want as an autonomous roboticist. A lot of these biologically inspired demonstrations are actually suffering from that problem, that they don't have a clear interface with how to give commands to robots. So interesting thing about comparing that to humans, and I'll come to that. So here, this is a video of the ancient 15 years ago when we had this project, and you can see that. So that is the fetus who was my group leader robotics at that time. He's now in the Fachhochschule, not far from here. He was leading this project where he's talking to the robot, and he was able to physically interact with the robot and tell it things. So like which screwdriver to grasp. Very simple. Actually very hard to get that going, I can say. And so here you would say the autonomy is just a way of how to program that robot, but at a high level. That is, I don't have to give it the detailed coordinates. I can tell it, give me the red screwdriver, and it figures out the details itself. Right? So you could say autonomy means defining an interface that is high level. And that is certainly something that is very attractive, and is efforts to achieve that in various forms that are not always going all the way down to very detailed motion planning, but that are providing high-level interfaces to robots. A lot of current deep learning kind of ideas are around that. So why do we do that? Why do we want to have autonomous robots? It's actually a real question, right? It's very different from industrial robots. So I actually did a little human experiment asking a lot of people, including my son, what would be good ideas for that. He said something about serving drinks, being cool, and robot soldiers was also an idea he had. And a couple of people I asked came up with ideas like that. And that's not stupid, actually. This is very close to what the actual situation is. I have a somewhat caricature view of that. I'm a little bit cynical about that, perhaps. So I would say a major field of the autonomous robotics that is close to deployment is useless as such, as toys, animation, fun, cool. Sometimes framed as possible therapy. There is really quite a bit of work about using robots in autism. Autistic people, for some reason, um, interact well with robots, while they have some problems, social problems. I'm talking about much more severely autistic than nowadays. Everyone says you're autistic, but people who have severe forms of autism are often, for instance, nonverbal and really cannot function. And they, for some reason, they react positively to robots. Nobody really understands why. So that would be a serious potential application. It's still research to see what that really can do. And you might know that there's this talk about companions and so on. And these are, of course, then essentially just animated toys. They are not really doing a lot, right? They're just moving. It's more the human who projects some emotion into that thing. And as you know, as a kid, you can take a wooden stick and pretend it's a human being. So it's not a lot of demand. You could even think that if it's too intelligent, you might even find it harder to take it seriously that way. But that is there are a lot of robots on the market, especially humanoids, that have no other purpose than that. And sometimes, like for a sales situation, they move a little bit. And there's Pepper. Some of you might know Pepper. He was actually used here in Bochum in I believe in this electronics store in the town center. I forgot the name of that. Saturn. In this company, they had a little greeting robot for a while. That was, or was it Balz maybe? So somewhere there on the sales floor, they had a little Pepper robot, just to say hello or something. It was almost nothing, but reacted when you're standing in front. Had a sensors when somebody was standing in front. So that's a whole line of work. I don't really know why that's being done. It's just somehow cool or something. The more serious version of that is assistance robots. So there is a lot of work especially in Europe on that, in an industrial context, very often in a medical context, like robots who would help in the hospital or, with aged people and so on. It's very interesting politically and socially that we're so much into the helping humans. So that turns out to be really, really difficult. The demands on autonomy, on perceiving the environment, in other words, has a human in there. And you have to perceive the human, understand the human, do something the human finds reasonable and so on. And maybe even physically supporting the human, like with handing parts or like lifting a patient. It's really difficult to do that, right? So there's a long history of European projects going through that direction. I would say very far from being deployed, but it's certainly an interesting problem. Autonomous vehicles are maybe the one case where it's really clear. You want the vehicle to move without wasting a driver, right? And that is a very attractive thing. And as you know, as I mentioned before, in the logistics domain, there is a lot of that, but not very autonomous. And then there's this view. Sorry, I had a slide here. I thought about cars. Maybe I deleted it inadvertently. Yeah, so I had a photo. I had that earlier. The autonomous driving for humans on the road is, of course, a major motivation just to save the human. And it would really transform the use of a car. If you had autonomous cars, then you wouldn't need to own one. It would be, most of cars are parked almost all the time. And you can imagine how much that would change the economy if you could use them 90% of the time, right? You wouldn't have to do parking, you would just drive somewhere and so on. So this vision was very interesting, and we were very engaged in that research for a long time. I had a group here that was working in this area, and myself am still involved in the company that does some work in this direction. But it turned out to be quite hard. Now, the one application that is really the best in terms of application use is the military one, which is somehow taboo here in Germany, even though it makes perfect sense. In the military, of course, don't have the need for a human there is very attractive, right? Because then you don't have the human in danger. And the military situation is one where detailed remote control is can be attacked. And you see this drone war right now in Ukraine. You see that the drones are having a major impact there, and they are usually not autonomous. They are remote controlled, and that remote control is vulnerable to attack, and that actually happens as we speak. As a real shift there, where these kind of countermeasures are being used, and the answer to that is autonomy. The Ukrainian army has developed already some. I don't know exactly who has done that, but the Ukrainian army is using robots that have an autonomous component that is, once they're close enough to the target, they will then navigate based on their own vision or some sensors we don't know, to achieve, hitting that target without remote control by a human operator. And that's very attractive, right? And it's something that really makes a lot of sense. And the US has a large military program. One of the most prominent researchers in this area, Ron Arkins, has worked very closely with the US Army, and some of that work isn't publicly known. So that makes a lot of sense. It opens up, of course, all kinds of questions. There are people who work on the ethics of that. Do you allow decisions like that? Good. So I will not really talk so much about that. So you see already that these are all, the military one is actually real. The vehicle one is not as real as hope. Tesla makes a lot of advertisement about autonomy, but it's largely misleading. So the real world consequences still always on the horizon. It's been for a long time. So I'm not sure that we can say it's such a major product line that tomorrow there will be a lot of autonomous robots deployed. So I would say autonomous robotics is a big field of engineering because it is also a very interesting research topic. And that, I think, is actually the major motivation for a lot of academics, including myself. And I wanted to say a few things about that. So it's a good playground for research. So why is that? So two theoretical reasons, and I'll mention then a practical one in a moment. So you could say there is, in modern engineering, this is true actually across the board, from civil machine to a lot of course, electrical engineering. And the core idea of modern engineering is that you have models that are model whatever you control or detect or whatever you do with it, so that the thing that is not described by that model is noise, is stochastic. And we have very good theory for that, for how to control that or how to signal that and so on. So often all communication is based on that, right? Communication, you're also in some sense controlling. You're sending on a signal and you have to make sure you send the signal so it can be detected. So it goes through all areas of engineering, right? And the models, engineers will know, it's sort of Kalman model would be the classical one, and now it's probabilistic models. And neural networks are very much used in that sense of more enlarged machinery for how to estimate properties of devices. And you could say autonomous robotics challenges this paradigm, because autonomous robotics, you could say, is about stuff that is difficult to model. When we say natural environments, what we actually mean is environments that are hard to model, right? If you have a factory floor and you have the plan of the factory floor, and you have a product that you have the CAD parameters of that product in your database, that's easy to model. And then we'll say it's not very autonomous. But if you go out into the office, or when humans are around, they're very difficult to model. Their behavior is difficult to predict. If you're out in nature, or if you're out, that's why military with the nature out there is very attractive, changing all the time. But off-road for vehicles, or just a typical environment, like an assistant robot would be in the environment a human is in, where stuff are it's cluttered, like a table like this. That would be really difficult to model. And so you're really forcing the limits of this classical paradigm. So that's one interesting challenge. And then the other theoretical challenge is ultimately integration or modularity. That if you think about a robot, I thought I had another slide here also. Yeah, here. Let's look at that first. So you think of what is needed to make a robot work. It's a lot of different things, right? Of course, you have to, at some point, you have some mechanical device which you control, and we're talking about controlling it based on perception. Perception, say more about that in a moment, uses some sensors, and then you want to do some planning, have some directedness for that, and you do that on some computer that is on the device, and there is communication on the device. There might be communication also with off-device stuff, and you have user interfaces. So all of these are different disciplines with different methods, and all of those have to be mastered. and they have to be integrated. They all have to talk to each other. So there's a lot of progress in robotics recently that is really just conventional software engineering of being better able to manage the system, to handle the system. At the same time, if you look at the software underlying these robots, it's kind of shocking how pedestrian a lot of that is, and that we need one doctoral thesis for getting one behavior going on a robot, and brittle large libraries, and they are not easily reused and all that. So this integration and how to modularize and system integration is a major challenge. So this is also one reason why autonomous robotic projects are often used as student projects. You have these robot soccer leagues, I don't know if you might know, that are often student projects, and they build their own little devices for that. My Portuguese connection, for instance, they're very big in that. In Germany, it's not as common that the students participate in these robot soccer competitions, which is, if you ever look at that, it's extremely boring. They're not very good soccer players, right, compared to humans. But it has that challenge. You have to handle all these different aspects, so very good training for the engineer. So for a long time, there was actually a whole discipline about architecture. So for instance, this is the classical sense, plan, act architecture, having some kind of idea of a unique flow from sensory input to action, and with world planning as a core element, so that there would be one level, that's a model of the world, including the agent itself, at which you would do the planning, which is still very much used in a lot of current systems under the label of deliberate planning that would have that kind of part. And there was a whole literature on people proposing different architectures like that with real time and so on. Actually sort of petered out because the discrepancy between the goals of that and the reality of what these robots could do was just too big. And the main bottleneck of was perception. And actually want to get there. Let me to the state of the art and tell you about the research projects here. I will have to see that I'm limiting my time here. So there's enormous research investment in autonomous robotics. If you go to meetings like IRIS or ICRA, it's almost all only about autonomous robotics. The conventional robotics is a small portion now of that. And it's been a sustained effort over many decades now. It has a little bit this characteristic like AI had for a long time, that it was always around the corner, that it always in the next generation is going to be better and so on, while the majority of products, for instance, you see at these meetings are still research platforms and not really platforms for deployment. I would say in autonomous vehicles, there has been a major breakthrough in the 90s and early 2000s, largely based on laser range finding and on probabilistic approaches. Actually, German researchers were very important in that. There is a group from Bonn who made a major breakthrough in this area, one of whom is now in the US at Stanford, and the other is in Canada, and the third Burkhardt is in Freiburg still. Combining probabilistic methods with these depth measurements. And that has pushed that to a new level where there was some confidence that autonomous driving was going to be possible. I think that the cooling of that idea is quite recent. So I would say most major players have pushed actual deployment of fully autonomous driving off now for the last 2 or 3 years only. And before, there was still the idea that it would happen very soon. But it was certainly enormous progress for a very long time. I can tell you that the reason why they hit a wall is this last 1%, right? It's all based on machine learning, right? You get a lot of data to learn. And then the data of these extreme situations that would be close to an accident are extremely rare, but still very varied. So there's a famous US study run by the Ministry, or financed by the Ministry of Transport, where they had fully instrumented a fleet of cars, I think like 100 or more. So measuring everything in a car and observing that for a year. And then they had like 36 accidents in this data set, which they ultimately classified into something like 14 categories, so less than 3 per category. And you see, it's very, very limited data to understand these extreme situations. I was involved in a project at Volvo where they were exactly about that. The idea was to model every class of accident and to have some user model for that and so on. And so the only thing would be always to see if one of these classes now suddenly applies. You can see it's very difficult. And so that is something that is inherently difficult, and it's ultimately a policy issue if you are willing to accept certain kind of accidents. As long as the percent of accidents be smaller in human drivers, then perhaps you could say, well, it's good enough. But the public acceptance isn't there. That is, if autonomous cars make accidents that a human would not make, even though overall they make a smaller number of accidents, it will still not be acceptable. This is currently the estimate that is happening. But still, autonomous vehicles has made so much progress that university researchers have largely left that area. I myself was in that area for a while, and I've left it, and we'll talk about it in the course. The first half of the course is about that. But we'll not talk about the latest methods because, you know, when things get very advanced, it's also very boring, a lot of detail. And engineers are willing to put all kinds of crazy stuff together to improve something. It's not very theoretically interesting. So we'll just talk about some core problems there. Now, in manipulators, I already mentioned that one problem is the perception, the demand on perception. There has been a lot of progress. You might not be aware, robot vision, using vision for robots, was out of fashion for many years. So nobody, especially when the laser rangefinder arose, everyone was going for that. And then there were some other methods. And it's only somewhat recent, maybe it's now already almost 10 years now, or it's like when deep learning started, the vision was rediscovered as a possible source. As you know, we humans use vision very extensively to do robotic tasks. And so that created some new enthusiasm, but I would say it's no breakthrough really. I go to these robotics meetings now, not every year, so with some intermittency, and I go see 2 years ago, and now, you know, it's really not a lot of progress. The other side of that is robotic manipulation, really dealing, you know, interacting with objects. And that is very hard, and it's not so clear if the progress in deep learning does much for that. There is a lot of work and there's interesting stuff going, but I would say still no cigar. I mean, a close friend of mine has been working in robotic hands. He actually developed a Pisa hand because it was done in Pisa. And that's now 25 years ago. And I would say the modern hands and the Pisa hand are not really that different. Right? So you can get maybe a sense for that if you, I don't know if you want to do that, but if you have, for some reason, don't have a sense of touch. Sometimes when you're extremely cold hands, you might have that, you know, or if it fell asleep, as we say, right? If you slept on your hand for a while, you have done no contact. You cannot do the simplest things with your hand if you have no sense of touch. It's also dangerous, by the way. You shouldn't try much because you can hurt yourself. And that is something that is totally outside the scope of almost all manipulation in robotics research. And there are some attempts, we actually ourselves have a arm that has a little bit of a haptic surface, or a little haptic sensor. Is awful. It doesn't work very well at all. We were quite disappointed. And but there's some work on artificial skin and getting some haptic sense for that. Imagine if you work with something you perceive rather than you have a model of, then you have some structural errors, and you might therefore have some unexpected, you know, amount of pressure or lack of pressure in contact, and therefore having some sense for how good your contact is would be really good. But that is not very developed. Actually, the human haptic sense is also one of the weaker areas of physiological research. There's actually a lot known about it now, but it's certainly complex. You know, many of you might not even know about the fundamental things about that now. How you use these little, you have these little structures on your skin. They're quite important for haptic sense. You're creating some acoustic waves when you're rubbing over something that gives you a lot of information. So this is a very interesting research project. And I would say the state of the art is that is one of the major areas of problems, and all kinds of ideas arise. Now there is a lot of real demand for manipulation. For instance, these big logistics companies now, Amazon was, the trailblazer for that, want to have robots to handle the stuff, right? In Amazon, you have a lot of humans actually picking stuff, putting it into places and so on. And they have robotomized that, and the solution is suction cups, right? Very, very crude suction cups. It's just something that grasps somehow an object and has a little vacuum, tube that makes the suction, and then you transport that. Right? So very crude, they not really modeling the object at all. And so on. Sometimes it will drop, and they have to deal with that. So that's sort of the state of the art, what is actually being deployed, rather than a precision grip. Very different from humans. If you look at small children, I have a granddaughter, you can watch right now. They do take a long time to learn manipulation. It's a long practice. So it's an inherently difficult process. So that's a major area. Okay, I end this introduction by pointing you to 4 core areas of challenge or research now within what I just said. Just also to say what I will be talking about more in the course. And actually, I will talk primarily about the last point, about movement generalization. So the first major challenge is, of course, perception. So just to make it a little sharper than we already talked about. So it's not just sensing, right? So perception is learning about the world, not learning about the stimulus. Often people. So if you just in technical terms, image processing would be working with the stimulus, right? And there are some contexts where that's what you do, like analyzing, I don't know, satellite data. Actually, even there it's not true, but sometimes medical data. But typically, what you want is you have some information, it can be auditory, it can be visual, and what you want is what caused that information, right? For instance, the 3D surfaces that caused that image to be like that, or the movement of the 3D object that caused a little movie like that. And that's what you need to know, because that is what enables action, right? So in computer vision, or called robot vision, it's finding out about the physical situation that gave rise to the images that you have. That's a undetermined or underdetermined problem. There could be always transformations on the world that give you the same image, like everything is further away and larger, gives you the same image. So that's just the simplest thing you can think of. So it's a non-determinate problem. You have to have some heuristics to solve that. And that's the major problem. So for instance, here, flash a little image, and you see this robot arm, for instance, that I showed earlier, right? And you will see it's the same kind of arm like this. And that is sort of a demonstration of a lot of things that you do there. There's all this cluster, and you have some way of maybe directing you. If I had said, where's the robot arm, and I had previously shown you what arm it is, you would have been able to find that relatively quickly, and you have it in a different pose, right? So it would be pose invariant recognition of that. And what you're doing is attentional selection. That is, you're attending to a particular object, a particular location. And that is something that current deep learning neural networks don't do. They don't have what is called visual search. It's not able, efficient way at least, to look for something specific in the image. They will very often be able to just do detection. That is, you give them an image and they can say, is there a dog in this image or not? And they can do this very quickly. But then they then have a way of finding out where the dog is. But if you tell them, find the robot arm, for instance, they don't have a very good approach to that. They have some workarounds. They can do detection everywhere and then look what voted for the detection, but it's not very efficient. And then also, other things like estimating then the pose of the object so that you will be able to act on it. So in the winter semester, I teach a little bit about that, but not so much from a robotic perspective, more from a psychological perspective of what the neural underpinnings of that are. So in this course, I don't really do much about that. And I think I want to skip that. A related problem. So in robotic research, there's a lot of the robotic research. People are now using deep networks for doing something interesting about that. Now, the other aspect is interacting with the humans. That's a wide area of research that overlaps with that, because often that is also about vision. And that has to do with the problem of joint attention or grounding of intentions. That is, it's not enough to have a language model, for instance, that can take the speech of the human and interpret the words. And as you know, the large language models you currently have would be able to predict what the next word is and so on. But of course, that's not what in a robotic scenario would be useful, because what you need to also know what the human is talking about. That is, which objects in that shared environment that you jointly attend is the human talking about, and what does he want you to do with what you're doing there. And that's sometimes called grounding, perceptual grounding of, for instance, language or relations. We do some research of that. For instance, this is from one of our papers where you will say the red cup to the left of the green cup. Right, and you know it's this one here. It's not that one here, and this is not a green cup to the left of which there is something. So this actually reveals it's already some kind of logic issue, that you could have hypotheses that you have to reject. This cup is a little larger, so you might actually first detect this one and then have to reject that. That's not a possible candidate for being the green cup we're talking about. So this very academic reduced thing, but just to illustrate that it's not actually trivial to do. And that's not state of the art. So you don't currently have systems that can communicate with a human using language, but also know in the world what the human is talking about. That's the real research here. And related intention perception is understanding from language what the user's intention is. And it's the intention of, again, grounded in the work, what the human is trying to achieve. And that's linked to the background knowledge problem. The background knowledge is maybe the most persistent and famous problem of artificial intelligence. It's this problem of implicit knowledge about the world. In classical AI, people were trying to develop models of background knowledge that would be for specific domains. This is what expert systems are supposed to do, right? Coding all the medical knowledge, for instance, in a particular expert systems. And there's been a lot of work, like knowledge networks, some knowledge graphs, and you might know that, where you have to list all the things you know about a domain and interrelate it into a bunch of graphs. And in robotics, there is a lot of background knowledge that's particularly hard to formalize. So, for instance, you know how to open a door. It's not trivial if you have to teach a kid to do that. But you also have things like knowing where milk is. It's in the fridge versus in some other cupboard, or how to grasp something, right? Which pose you use for which action. Also, maybe how hard to grasp something. You will grasp an egg differently than maybe a weight that's heavy. How to put down something. If you want to put something on the surface, you have to have some idea how much space do I need for that? What would be a good place to do it? Maybe not driving where my elbow is. And actually, more subtle things that I'm not sure I have that slide in here. More subtle things like how hard, if you're human, you're going on the surface, you know that if it's on slippery grass, you would accelerate a little more slowly and go a little bit more smoothly than if you're walking down, I don't know, in high heels on a rigid surface, like clack, clack, clack. So there's also a form of knowledge that you have, right? And that's knowledge is particularly hard to formalize. And so this problem of background knowledge shows up in the autonomous robotics domain, in that these robots are very, very specialized. You have a robot demonstration, a robot that can fry an egg. No, there's literally actually a lab in Bremen who did that as a project. And then, two PhD students work on that for 2 years, and then it can actually really fry an egg. If you do just a little change, then there's another PhD thesis to boil an egg or whatever it is. And that is because they have to program all that background knowledge, how to open egg, egg is a fragile object, how to do that it breaks just right at the right time, and all that. So that's a big problem. There is the kind of problems that people do is classically about how to represent knowledge, how to reason on such basis, how to do planning on such basis, and so on. But I would say, I'll skip that. I'll say that currently the work is really about what's called autonomous learning, that a system learns from experience online, people also call that online, that is while it's behaving, it has to learn. But also continuous learning. That's a really interesting research frontier. There's a lot of work on that currently, where you also have a lot of pre-structuring from large data sets, and then you want to update your model based on some real-time experience. Yeah, and finally, movement generation. So movement generation is sort of the core problem of robotics, of course, and that's what we're really talking about more here. So I will actually not have very interesting things to say about background knowledge. The thing I skipped, yes, sometimes we can put into the architecture some knowledge about what are elementary behaviors. We'll get a little bit of that. So I'm not doing perception, I'm not doing a lot of interaction, I'm not doing background, but I'm doing primarily movement generation, which is of the simplest part of it. And so movement generation classically is about planning and control, and classically they are different. Now, planning is knowing about the constraints and designing time courses that achieve those things. And the control is just physically realizing them. And I already hinted at arguments why in autonomy that's hard, because the perceptual demands for planning are very, very high, and control is difficult when you have compliance, the constraint of compliance and doing it softly. And we often also really want to do it human-like. And therefore, the alternative approach that I will be teaching about a little bit in the second part of the course is about human-like movement, or movement that is inspired by how animals and humans move. So that's, I will mention that in one lecture that will be about navigation in animals, so how animals know where they are and plan to be other places. And you'll see there's a close analogy to our methods. And then I'll look at movement planning with studying consistent kinds of ideas. So the idea there is that planning and control are not so separate, that you're doing planning in control style. That will be sort of the idea. And that has to do with timing and coordination also, that the time course of the planning is part of your plan. It's not separate. That's sort of the main emphasis of this course. Good. So yeah, we don't need that. And so, yeah, I want to end on emphasizing this. So in that sense, this is not a standard autonomous robotics course. That if you take a textbook on robotics, autonomous robotics, there will be some overlap. I would say 50% perhaps is overlapping, but a lot of this is really about this analogy to animals and nervous systems, how we solve problems like that. So in the classical sense, I'll give you a review of vehicle path planning and a review of the basic concepts of robotic manipulators, planning and control. So that's a total of about 3 lectures that are overlapping with classical thinking, and the rest is much more specific in this dynamic systems perspective. Yeah, I put a little chapter to read. It's just 3 pages, an introduction to our book that throws some light on that. And then I will be talking about timing, movement generation with muscles. And then here I will be talking about attractor dynamics and some related approaches. So this is the navigation analogy I mentioned. This is classical, that's classical, and that is sort of non-classical, and this here is non-classical. And so that's sort of the survey of the course. So I will try to do an essay when we're done here with this first part. So you will be having a chance to get that first part, attractor dynamics of for vehicles, get a good handle of that, and have some reading about that. And it's also quite relevant for the exam. And then these 2 will also be something that you can easily, so textbook like that you can do for the exam. And here toward the end, this will become more research oriented and something that you don't have to understand in every detail. That's so sort of a gradient that toward the end of the course, there are things that are more for intellectual stimulation than textbook knowledge that you will have to have later. Yeah, so I think I'm out of time. So people could feel free to leave, but I'm also very happy to answer questions and also to answer organizational questions I still have.